The seafloor came up through the hull. 31 people had sailed from Tokyo the day before to put a new island on a chart. What floated back was volcanic glass. This is the Ogasawara Arc, the water Japanese crews call Ma no Umi, the Sea of the Devil, running south toward Iwo Jima. The obvious answer is undersea volcanoes, and it is wrong because that volcano was not erupting when they arrived. Something here kills people who do everything correctly, and the record runs from feather hunters in 1902 to a wave in 2023 nobody explained for 11 days. Start with the administrative fact, because it quietly shapes everything else. The water where that ship died is Tokyo. Not near Tokyo, Tokyo. Buy a ticket at Takeshiba Pier, in the middle of the city, sail south past the container terminals and the bay traffic, and you will still be inside the same metropolitan government a full day later, in open ocean, with no land on any horizon. Tokyo Metropolis administers a chain of islands that runs roughly 1,000 kilometers into the Pacific, and then keeps running past Chichijima, past Hahajima, down to Iwo Jima and Minami Iwo Jima, which sit another 300 kilometers beyond that. On a municipal map, it reads as one jurisdiction with an unusual shape. On the water, it is a different planet with the same postcode. There is no airport at Ogasawara. There never has been. The islands were returned to Japan in 1968 after 23 years of American administration, and in the decades since, every serious proposal to build a runway on Chichijima has died on the same three obstacles. The terrain is steep volcanic rock with almost no flat ground. The surrounding water and forest have carried a World Heritage listing since 2011 that a runway would compromise, and the money involved for a population of roughly 2,500 people has never survived contact with a budget committee. So the connection to the rest of Japan is a ship. One ship. The Ogasawara Maru sails from Takeshiba, takes about 24 hours to reach Futami Port on Chichijima, and then usually waits 3 days before sailing back, which means the service runs roughly once every 6 days. Sit with what that schedule does to a human being. If you break your leg on Chichijima on the wrong afternoon, the fastest scheduled route to a mainland hospital may be 5 days of waiting followed by a day at sea. If you have appendicitis, that arithmetic kills you. So Japan solved it with an aeroplane that does not need a runway. The Maritime Self-Defense Force flies the US-2, a 4-engine amphibian designed to put itself down on the open ocean, and its 71st Air Squadron has been running emergency medical flights to these islands for decades, first with the older US-1A, and now with the newer machine. The aircraft covers the 1,000 kilometers in roughly 3 hours. It lands on the sea near the island, a small boat carries the patient out, and the patient is hoisted aboard from a rolling deck onto a rolling aircraft. That is an extraordinary capability, and it comes with a hard physical ceiling. The US-2 is rated to operate off the water in waves up to about 3 meters. Above that, the airframe is not landing, no matter how sick the patient is, no matter how much fuel is aboard, no matter what the doctor on the island says. 3 meters is not a storm. 3 meters is a windy Tuesday in winter across most of this ocean. Hold that number, because it is the cleanest way to understand the whole region. The limit on saving a life out here is not the technology, and not the will, and not the distance. It is the shape of the water on the day. Notice what the ocean is doing there. It takes ordinary problems, the kind that a city solves in 40 minutes with an ambulance, and it stretches them until they become survival problems. Now scale that up from one patient to a ship in trouble, and the picture gets worse fast. The Japan Coast Guard keeps an office and a patrol vessel at Chichijima, and that vessel is responsible for an area of ocean larger than most countries. If something goes wrong 300 kilometers from Futami, the nearest help is not an hour away. It is most of a day away, and it is coming through the same sea that caused the emergency. So the honest question at the start of this story is not why ships have died along this line. It is how anyone was ever expected to survive an accident here in the first place. And the answer to that question is buried in the shape of the seafloor, which is where the real machinery is. Draw the line properly. From Tokyo Bay, the volcanic islands go south in a nearly straight file. Izuoshima, Toshima, Niijima, Kozushima, Miyakojima, Mikurajima, Hachijojima, Aogashima, then the Bayonnaise Rocks, then Smith Island, then Torishima, then Sofugan, then a long gap of open water, then Nishinoshima, then Kita Iwojima, Iwojima, Minami Iwojima, and the shoals beyond. Above water, that file looks thin and harmless, a scatter of green and gray dots on a wide blue field. Below water, it is a single continuous mountain range about 1,000 kilometers long, and only its highest peaks break the surface. Japan's official register of active volcanoes lists 111, and a startling share of them are not mountains you can walk up. They are seamounts, and their summits are underwater. And they have no names in ordinary conversation because ordinary people have no reason to know them. Parallel to that mountain range, roughly 200 kilometers to the east, is the reason it exists. The Pacific Plate is sliding down under the Philippine Sea Plate along the Izu-Ogasawara Trench, and it is doing so at something like 4 to 6 centimeters a year, a little faster than a fingernail grows. The crust going down here is old, some of the oldest seafloor left on the planet, which makes it cold and dense and heavy plates sink steeply. That single fact about the age of the rock is why the trench alongside Tokyo's island chain is one of the deepest features in the ocean. Soundings put its floor at roughly 9,780 meters. Take the tallest mountain in Japan, drop it in, and the summit of Fuji would still be about 6 kilometers beneath your keel. Here is where the arithmetic turns strange. That 9,000-meter trench and those volcanic peaks are not far apart. Within an afternoon's steaming, you can go from water so deep no light has ever reached the bottom to a seamount whose summit sits a few tens of meters below your hull. Fukutoku Okanoba, far to the south, has spent long stretches of its recorded life with its top around 25 meters under the surface. That is shallower than many harbors, and the transition between those two states is not a gentle slope. It is a wall, which produces a set of practical consequences that most sailors never have to think about, because most seas do not work this way. There is no continental shelf here. A ship working off Hokkaido, or in the Yellow Sea or across the North Sea has hundreds of kilometers of shallow ground under her. And shallow ground means options. It means you can anchor. It means a fishing boat can sit out weather in 100 meters of water with cable down and ride it. It means a disabled vessel does not immediately begin drifting towards something worse. Along the Izu-Ogasawara line, almost none of that is available. Outside a small handful of bays, you cannot anchor, because the bottom is either a kilometer down or it is a vertical flank of volcanic rock that will foul your gear and hold it. There is also no shelter. Look at where the harbors are along this chain, and the honest count is short. Futami Bay, on Chichijima, is a genuine sheltered anchorage, which is exactly why the Imperial Navy valued it and why the ferry terminates there. Hachijojima has a working port with a hard limit on sea state. Aogashima, which has about 170 residents, does not have a real harbor at all. Its landing is a concrete apron at the base of a cliff, and when the swell runs, the ferry does not come, and the small crane that lifts cargo and sometimes people simply does not operate. Islanders there measure their year partly in how many days the boat could not land. Now put those two facts together, and you get the first real rule of this ocean, which is going to be violated repeatedly at enormous cost by people who had every reason to believe otherwise. In most of the world, when things go wrong at sea, you look for shallow water. Shallow water means land, and land means help. And even if the ship is lost, you have a chance of standing on something. Down this line, shallow water means you have found the top of an active volcano. The shallowest ground in this entire region is, statistically and physically, the most likely ground to try to kill you. The chart symbol that looks like relief is the hazard. That inversion is not an abstraction, and it is not a clever way of putting things. It is the specific, documented mechanism that destroyed a Japanese government survey ship with 31 people aboard in 1952, and it is a mechanism nobody understood at the time, because in 1952 nobody had a reason to expect that a volcano gets more dangerous as it comes closer to the surface, not less. Before that, though, there is the water itself, moving. Because a stationary chart, however alarming, does not kill fishermen in ordinary weather, and this sea has been killing fishermen in ordinary weather for as long as there have been records to keep. The current that runs up this chain is called the Kuroshio, and the name is literal. Kuro is black, shio is tide. It is called the black current because that is what it looks like from a deck. The water it carries up from the tropics is so poor in plankton and suspended sediment that light goes deep into it and does not come back, and the surface reads as a hard indigo that stands out against the greener coastal water beside it. Crews can see the boundary. There are days when you can watch it pass under the hull as a line. Physically, it belongs to the same family as the Gulf Stream. It is a western boundary current, which means the rotation of the planet and the shape of the ocean basin squeeze the return flow of the North Pacific into a narrow, fast ribbon on the western side. It comes north past Taiwan, pushes through the Tokura Strait, runs along the south coast of Japan, and then crosses the Izu Ridge, the same submarine mountain range we have been talking about, before turning east into open ocean. In its core, it moves at roughly 3 to 4 knots, occasionally more. It carries something on the order of 50 million cubic meters of water every second, which is more than every river on Earth combined, by a wide margin. 3 to 4 knots does not sound frightening. Most people hear it as a brisk walk. For a fishing boat making 8 knots, it is the difference between a 5-hour run and a 9-hour run, which matters for fuel and for daylight, but does not sound like a threat to life. The threat is not the speed. The threat is what happens when that mass of moving water meets wind coming the other way. Here is the mechanism. And it is worth getting right, because it is the single most common way people die in this ocean, and almost nobody outside the industry can explain it. A wave in deep water is not a wall of water traveling towards you. It is a shape moving through water that is mostly staying where it is. What matters about that shape is not only its height, but its spacing, the distance from one crest to the next, and the time between them, which sailors call the period. A swell 3 meters high with 14 seconds between crests is a long, low hill. A boat rides up it and over it and down the back, and the deck barely moves relative to the horizon. Now take exactly the same 3 meters of height and compress the spacing so that crests arrive every 6 seconds. Nothing has changed about the height. Everything has changed about the ride. The face of the wave is now steep instead of sloped, and the boat no longer has time to lift. The bow is still coming down from the last crest when the next one arrives, so the wave hits the hull instead of passing under it. Opposing current does exactly that compression. When waves run into a current flowing the other way, they slow down relative to the ground while their energy stays in place. So the crests bunch up. Wavelength shortens, height rises. Steepness, which is just height divided by wavelength, climbs on both counts at once. Push it far enough and the wave becomes physically unable to hold its own shape, and it breaks in open water, with nothing shallow beneath it. And there is a hard threshold in this. When the opposing current gets strong enough, relative to the speed of the waves cannot advance against it at all. They stop and stack, and the energy that should have traveled onward stays where it is and goes into height. Now put the winter on top of it. From roughly December through February, cold, dry air pours off the Asian continent under the Siberian high and blows out over the Pacific, over the Izu-Ogasawara chain that arrives as a persistent northerly, and the Kuroshio is setting northeast. Wind against current for weeks at a time, across 1,000 kilometers of open water with no coast to shelter behind. The forecast for such a day can read as entirely unremarkable. Wind 25 knots, seas 3 meters. In most of the world, that is a working day for a fishing boat. On the Kuroshio front, it can mean short, steep, breaking seas that hit a 20-meter hull as impacts rather than motion. And the same current does something else in winter that turns the whole thing vicious. The Kuroshio is warm, carrying tropical surface water north at temperatures around 20 degrees Celsius and higher, and in January it is doing that directly underneath air that has just come off Siberia at well below freezing. That temperature difference is one of the largest air-sea contrasts anywhere on the planet, and it pumps heat and water vapor into the atmosphere at an enormous rate. Storms feed on exactly that. The band of ocean south and east of Japan is one of the most productive places on Earth for explosive cyclogenesis, the process in which a low-pressure system deepens with startling speed, sometimes dropping 24 millibars in 24 hours. Crews have a phrase for the result in Japanese weather bulletins: a low that develops rapidly. It means a system that was a smear on yesterday's chart and is a storm on today's. So the current steepens the waves. And the current also builds the storms that make the waves, and it does both in the same season, over the same water, along the same line of islands with no shelf and no anchorages and no shelter. That is not a coincidence, stacked on a coincidence. It is one machine with several outputs, and the machine is not bolted down. The Kuroshio does not follow one fixed line up the coast of Japan. It has two stable paths, and it switches between them, and what largely decides which one it takes is the Izu Ridge, the same drowned mountain range that makes this whole region what it is. In one state, the current runs close in along the southern coast. In the other, it swings out into an enormous southward loop, hundreds of kilometers offshore, before rejoining. The switch is not gradual, it is not forecastable more than a season or so ahead, and once it happens, it can hold for years. The large meander that set up in August 2017 became the longest continuous one in the record, running on year after year after year. For anyone working this water, that is not oceanographic trivia. When the current moves, the fishing moves with it, because the fronts and eddies that concentrate a catch are attached to the current and not to the seafloor. Coastal water temperatures change, and with them which species turn up and when. And the sharp water, the front where a moderate northerly stops, being a moderate northerly, and starts breaking on deck, relocates to a piece of ocean that may be nowhere near where a skipper's 20 years of experience says it should be. So even the current is a moving target. That matters more than it sounds. Because nearly everything that goes wrong in this story turns on a competent person making a reasonable judgment about a stretch of sea that has quietly stopped being the stretch of sea they learned. There is one more output, and it is the reason people keep going out there anyway. Seamounts are fish factories. When a fast current runs into an underwater mountain, it cannot go through. So it goes around and over, and that deflection drags deep water upward. Deep water is loaded with the nutrients that surface water has been stripped of. Bring it into the sunlight and plankton bloom, and everything that eats plankton arrives, and everything that eats those arrives after that. Around the tops of these seamounts, the water gets caught in slow rotating pockets that hold the bloom in place instead of letting the current carry it away. The result for a fishing crew is not subtle. It is the difference between an empty ocean and a full one. In a very small area, in a very specific place, you can find again. Which means the most dangerous ground in this ocean is also the most valuable ground in this ocean, and it is dangerous and valuable for exactly the same reason. The mountain that concentrates the fish is the mountain whose summit is a few tens of meters under the surface. The current that makes the fishing good is the current that turns a moderate wind into breaking seas. There is no version of this where a crew can take the profit and decline the hazard. The two are the same object. That is why the tuna and skipjack fleets worked the Izu Ogasawara grounds hard through the 20th century, and it is why a fishing boat, not a research vessel, and not a warship, was the first to see what happened at the Bayonnaise Rocks in September 1952. They were there because that is where the fish were. They were there because that is where the mountain was. Understand what these boats were. In the years after the Second World War, Japan rebuilt its fishing fleet at speed because the country needed protein and needed export earnings and had a coastline full of men who knew how to catch fish. A great many of the vessels working the southern grounds in that period were small, wooden, under 100 tons, crewed by 5 or 10 or 15 people. Radio was not universal, and where it existed, it was often a low-power set with a range that depended on the time of day and the state of the ionosphere and whether anyone happened to be listening on the other end. A boat 200 miles south of Hachijojima with a modest transmitter and a failing engine was not in contact with anybody. She was simply late. That word matters more than it sounds. Late is the normal state of a fishing boat. Late is weather, or a good school of fish, or a fouled net, or a bearing that needed nursing. A boat that has not come back on the expected day is not, on that day, a search and rescue case. She becomes one when late turns into overdue, and overdue turns into a formal report, and the report turns into aircraft in the air. And by then, it is often 48 hours or more since anything went wrong. In an ocean where a person in the water in winter has hours, not days, that delay is the whole story. So the pattern that would later get labeled supernatural has an unglamorous shape at its base. Small boats, working the richest and roughest ground in the region, in the season when the wind fights the current, out of radio contact, in an area where nobody notices you are missing until you have been missing for a long time, and where the water is too deep to leave wreckage anywhere findable and too fast to leave it anywhere near where it started. Take 100 boats in 5 years and you will get losses. Take those losses and put them on a map without the fishing grounds, without the wind, without the current, and without the dates, and you will get a mystery. We will come back to that map because a man in the United States made a great deal of money drawing it badly, and another man took it apart with a filing cabinet and a stack of letters, and in doing so, he accidentally made the real hazard invisible for a generation. But none of this began with fishing fleets or research ships. It began with people who had no engine, no radio, no chart, and no choice, and who worked out the rules of this ocean the hard way in the 1840s on the bare cone of the very volcano that would later kill everyone who tried to live on it. In January 1841, a small fishing boat put out from the coast of Tosa, on the island of Shikoku, with 5 people aboard. The oldest was a man named Fudanojo, in his late 30s, who was in charge. With him were his brothers Jusuke and Gomen, a man called Teraman, and a 14-year-old hired for odd jobs because his father was dead and his family needed the money. The boy's name was Manjiro. He had no particular skills. He was there to carry things and bail. They were caught by weather offshore and lost the ability to work back toward the coast, and then they crossed into the black water. Every fisherman on that coast understood what that meant. The Kuroshio is not a thing you cross back over in a small, open boat. It is a river 3 or 4 knots wide in a sea where a rowed hull makes 2. And once you are inside it, your destination is no longer a decision you get to participate in. Japanese coastal communities had a word for people this happened to, and enough of it happened that the word was in ordinary use. Castaways from these islands turned up in the Aleutians, in Hawaii, on the American coast. The current does not lose you. It delivers you somewhere else on its own schedule. For Manjiro's boat, the delivery address was Torishima. They were on the water for days. The boat broke up on the rocks of an uninhabited volcanic cone about 600 kilometers south of what is now Tokyo, and all 5 of them got ashore. Jusuke's leg was badly hurt in the wrecking, which meant that from the first hour, they were a group of 4 working people and 1 who could not walk. Torishima is not a hospitable place, and the reason it is not matters. It is a stratovolcano, roughly 2.5 kilometers across, with a summit a little under 400 meters, and the entire island is the volcano. There is no interior. There is no soil worth the name. There is no stream, and there is no spring, because rainwater goes straight down through porous volcanic rock. What there was in 1841 was birds. Torishima was one of the last great breeding colonies of the short-tailed albatross, a seabird with a wingspan over 2 meters that nests on open ground, and, having evolved with no land predators, does not run away from an approaching human being. That single behavioral fact is the reason 5 castaways lived. They could take birds by hand. They ate albatross and seaweed and shellfish off the rocks, and they drank rainwater collected out of hollows in the lava, and they sheltered in a cave. They did this for about 143 days. Then, on the 27th of June, 1841, an American whale ship called the John Howland, out of Fairhaven, Massachusetts, under Captain William H. Whitfield, came into the island looking for turtles and found 5 Japanese men on the beach. What came out of that meeting is one of the strangest careers in the 19th century, and it is directly relevant. Japan at that time was closed. Returning home from a foreign ship was, on paper, a capital problem. So Whitfield carried them to Honolulu, where 4 of them stayed, and the boy, who had made an impression, stayed with the ship and then with the captain and sailed to Massachusetts. Manjiro went to school in Fairhaven. He learned English, mathematics, navigation, and surveying. He went whaling again and rose to first mate. He worked the California gold fields specifically to earn the money for a passage back. In 1851, he bought a whaleboat, had himself dropped in the Ryukyu Islands, endured months of interrogation by officials who had every reason to be suspicious of a Japanese man arriving from America, and eventually got home. 2 years after that, Perry's squadron arrived in Edo Bay, and the government of Japan discovered it possessed 1 man who had lived in the United States, understood American ships, and could read a navigation manual. He was raised to samurai status and put to work. Hold on to the shape of that story, because the reversal in it is not sentimental. It is structural. The thing that saved those 5 men was an active volcano covered in birds that had no fear of humans. Both halves of that sentence were about to become lethal. The birds first. A colony that lets a starving castaway walk up and take dinner by hand is a colony that lets an organized commercial operation kill 5 million of them in 15 years. And the volcano, which for 143 days was simply a rock that happened to be above water, was not dormant in any meaningful sense. It was between eruptions. Nobody on that island in 1841 had the information to tell the difference. And in fairness, nobody in 1902 did either. Before the feather hunters, though, there is a case 60 years earlier that shows the entire pattern already running, on a different island in the same chain, with a documented outcome and a documented decision afterward that most people find hard to believe. Aogashima sits about 60 kilometers south of Hachijojima and is one of the more extraordinary inhabited places on Earth. It is a volcanic island roughly 3.5 kilometers across, and its whole interior is a caldera, with a smaller cone rising inside it, so the village sits in a bowl inside a bowl with cliff walls on every side. There is no natural harbor. There has never been one. Cargo and people come ashore against the foot of a cliff when the swell allows it, and often it does not. In the 1780s, roughly 327 people lived there, farming, and fishing. The volcano began showing itself in 1780 with steam and ground movement, and worsened through 1781 and 1782, and the islanders kept living with it, because their houses and fields and graves were there, and because the alternative was to abandon everything on the strength of a smell and some shaking. In the spring of 1785 it went properly. Ash, fire, and eruption on a scale nobody there had experience of, on an island where the only exit is a boat that has to be launched off rocks into open ocean. They tried to evacuate under those conditions. Roughly 200 people got off and reached Hachijojima. Roughly 130 to 140 did not. That is close to half the population of the island, and it is a number produced not by the eruption alone, but by the geometry of the place. An island with no harbor cannot be evacuated quickly, and an evacuation that cannot happen quickly happens during the emergency, rather than before it. Aogashima was then abandoned, not for a season, for about 50 years. The survivors lived as refugees on Hachijojima, where they were, by the accounts that survive, not especially welcome and not especially prosperous, and where a generation grew up who had never seen the island their parents talked about. And they went back. The return was organized over decades, argued through officials, funded, staged, and completed around 1835 under a village headman named Sasaki Jirodayu, whose name is still attached to it on the island today. People sailed back to a live volcano that had killed half of them and rebuilt the village inside the crater, and their descendants are there now. About 170 people live on Aogashima today, inside a caldera that Japan's meteorological agency lists as an active volcano. That is not recklessness, and reading it as recklessness will make everything that follows incomprehensible. It is land. It is the only land those families had a claim to. 50 years of being poor guests somewhere else is a genuine, grinding, generational cost. And set against it, a volcano that has been quiet since 1785 is an abstraction. Human beings consistently trade a certain present loss against an uncertain future one. And they are not being stupid when they do it. They are being people. So the rule that the rest of this story keeps proving was already established before anyone in this region had an engine or a radio. These islands are dangerous in ways that are slow and intermittent. They produce something valuable enough to justify the risk, and the intervals between disasters are long enough that the risk stops feeling real. The gap between eruptions is not a safety margin. It is a recruitment period. And there is a second rule, quieter, that came out of the same century. The people who did best in this ocean were the ones who adapted their schedule to it rather than the reverse. Coastal fishermen worked seasons, stayed inside known distances, read the watercolor and the temperature under their hand and the behavior of birds, and treated the black current as a boundary you do not casually cross. That is not folklore. It is a working observational system built out of thousands of trips, and it encodes the single most important fact about this region, which is that certain failures here are not recoverable. Not difficult, not expensive, not recoverable. You do not row back across the Kuroshio. Everything that goes wrong from this point forward involves someone with a schedule that came from somewhere else. A feather contract with an export deadline. A scientific survey with a landform that might vanish. A transport flight with an arrival slot. A ferry timetable. In every case, the schedule was reasonable, the people were competent, and the ocean did not adjust. The first of those schedules belonged to a businessman from Hachijojima, and the product was feathers. Tameoki Han Emon was born on Hachijojima in 1838 and spent his working life turning remote Pacific rocks into revenue. He had already been active in the Ogasawara Islands when he turned his attention to Torishima in the late 1880s, and what he saw there was not a volcano. It was inventory. The short-tailed albatross bred on that island in numbers that are hard to hold in the head. hundreds of thousands of birds, possibly more, nesting on open volcanic ground in dense colonies, arriving in autumn and leaving in spring, and completely unafraid of anything walking toward them on two legs. Their feathers and down were worth real money in the Meiji economy. Down filled bedding and pillows domestically, and the export market for feathers was strong, feeding a Western fashion industry that was consuming birds on an industrial scale in that period all over the world. Feathers were light, dense in value, non-perishable, and could sit in a warehouse on an island for months waiting for a ship. For a business operating 1,000 kilometers from anywhere, that combination is close to ideal. So he built a settlement, not a camp. A settlement with houses, storehouses, cisterns to catch rainwater because there is no fresh water on Torishima, and a shrine. Workers came from Hachijojima and elsewhere on contracts and lived there through the season and often through the year. Supply vessels called. The operation ran for about 15 years, and in that period, the estimate that appears again and again in the ornithological literature is that roughly 5 million short-tailed albatrosses were killed on that island. The killing was done with clubs, because that is all it required. Birds that do not flee do not need to be hunted. They need to be processed. State that plainly and move on, because the point here is not moral outrage at people a century dead who were doing legal work for wages. The point is what an operation like that tells you about the island's economics. 5 million birds is not a side business. That is a resource stream large enough to justify almost any level of inconvenience. And inconvenience was the only category anyone had for the volcano, because they knew it was a volcano. That is the part people get wrong. Nobody on Torishima was laboring under the impression they were on an ordinary island. The ground was hot in places. There were fumaroles putting out steam and sulfurous gas. The whole cone smelled of it in the wrong wind. And the operation's response to that information was not to leave. It was to mine the sulfur as a second product, because sulfur was worth money too. The warning sign became a revenue line. That happens more often than anyone likes to admit, in more industries than this one. Now look at what the settlement could not do, which is the part that decided the outcome. There was no harbor, because Torishima is a cone dropping steeply into deep water with no shelf and no bay. Landing was by small boat through surf onto rock, weather permitting. There was no telegraph and no radio because it was 1902 and neither existed on an island like that. There was no vessel permanently stationed there capable of taking 125 people off in a hurry. And there was no monitoring of any kind. Nobody was measuring ground deformation or gas output or seismicity because nobody anywhere was doing that yet in any systematic way. And even if they had been, the data would have had nowhere to go. Put those 4 absences together and you have a community whose entire safety plan was that nothing would happen. Not a bad plan exactly, just a plan with one assumption in it. In August 1902, Torishima erupted. It was a substantial explosive event that reshaped part of the island. Everyone living there was killed. And here the record gives us 2 numbers instead of 1. The Yamashina Institute for Ornithology, which has worked on this island and its birds for decades, gives the figure as 125. Other accounts put it at around 150. That discrepancy is not sloppiness by historians. It is what happens when a labor force on a remote island includes seasonal workers, contract workers, and family members, when the payroll records are on the island, and when there is nobody left to count. Both figures appear in serious sources. The honest thing is to say the settlement's population was somewhere between about 125 and 150, and that the survival rate among the people on the island was 0. There were no witnesses, not one. That deserves a moment, because it is going to become a theme with real consequences later. Everything anyone knows about what happened on Torishima in August 1902 is reconstructed from the outside, from the state of the island, when a ship next arrived, and from the geology written into the ground afterward. No log, no letter, no radio call, no survivor. The event did not merely kill the people. It deleted the account of itself. Hazards of this kind have that property, and naming it now explains a legend that is still circulating. In most disasters, something reports back. A ship sinking in the Atlantic leaves boats, bodies, wreckage, and a distress call. A volcano that detonates a settlement on a bare cone in the middle of the Pacific, or a shoal that detonates under a ship's keel, leaves an absence. And absence is the raw material out of which mysteries get manufactured. Hanemon Tamaoki was not on the island. He was in Japan when it happened, which is the reason there is a man to talk about it all. He lost his entire workforce and his entire installation in a single morning. He restarted operations the following year. Read that again, because it is the cleanest statement of the mechanism this whole story runs on. 1 year after an eruption killed every person in his settlement, the same business was back on the same cone, killing the same birds, and hiring more people to do it. Feather harvesting on Torishima continued, on and off, for another 3 decades. Tamaoki died in 1910, and the operation outlived him. Judge that if you want, but understand it first. The value did not change. The birds were still there and still worth money. The market was still buying. The workers still needed contracts. And the volcano, having just erupted, would have looked to any reasonable person in 1903 like the safest it had been in years, because that is precisely how human beings misread volcanoes. A mountain that just went is a mountain that just spent its energy. That intuition is completely understandable and completely unreliable. And there is a version of that same mistake at the center of the 1952 disaster, made by professional scientists with far better information. The birds paid for it worse than anyone. By the early 1930s, the harvesting had run the short-tailed albatross down toward nothing, and in 1949 a survey found no birds at all. The species was written off as extinct. Then in 1951, on that same island, about 10 birds were found nesting. 10. A species that had numbered in the millions on that one slope within living memory came through the 20th century as a rounding error. And it came through on the flank of the volcano that had killed the people who exterminated it. And the volcano was not finished making the point. In 1947, Japan established a meteorological observatory on Torishima, staffed by professionals whose entire job was measuring the physical world, on an island the state now understood perfectly well to be active. That station operated for 18 years. In 1965, renewed volcanic activity forced the staff off, and they never went back. Torishima has had no permanent human population since. The state itself, with a trained team and a specific mission and a supply line, ran the same experiment the Feather Company had run, and reached the same conclusion by the same method. You cannot hold this island. You can only visit it, which is now, in the least likely turn in this entire story, exactly how the albatross survives. The colony that came back from 10 birds re-established itself at a place on the island called Tsubamazaki, and Tsubamazaki is a slope of loose volcanic ash on an active cone, which means it slides. Nesting ground washes away. Chicks are buried. The ornithologist Hiroshi Hasegawa, who has worked on this colony since the 1970s, and the teams around him, responded by trying to move the birds. They set out painted decoys and played recorded calls on a more stable part of the island to persuade albatrosses to nest there, and they physically relocated chicks. It worked. The population has climbed back into the thousands. Think about what that means. The last stronghold of a species that human beings nearly wiped out is now managed by human beings hauling chicks across an active volcano to keep the volcano from taking them. On an island where no person is allowed to live, reachable only by boat in the right weather, with no harbor, 600 kilometers from Tokyo. That is not a heartwarming ending. That is the same hazard system running. with the objective changed from profit to preservation and the constraints identical. So by 1902, the pattern was fully visible to anyone willing to look at it. Value pulls people onto the vent. The vent is quiet for long enough that quiet reads as safe. Distance and the absence of a harbor remove the ability to leave in a hurry. And when it goes, the event erases its own witnesses. What nobody had established yet, and what would cost 31 more lives 50 years later, is that this arc does something considerably more dangerous than erupting on schedule under people who live on it. It builds brand new ground in open water, advertises the fact, and is at its most explosive precisely at the moment the new ground appears. About 400 kilometers south of Tokyo, 60-odd kilometers beyond Aogashima, there is a small group of rocks sticking perhaps 10 meters out of the ocean. They are called the Bayonnaise Rocks, after a French warship that reported them in 1850, and on a chart, they look like nothing at all. 3 or 4 black specks with a depth figure beside them. They are not nothing. They are the highest surviving fragment of the rim of a submarine caldera roughly 10 kilometers across, which is to say those 10 meters of rock are the visible corner of a volcanic structure the size of a city that failed and collapsed at some point in the geological past. Inside and along that rim, new cones grow. One of them, on the eastern side, has spent the last 70 years going up and down through the sea surface, like something breathing. On the 17th of September 1952, a fishing boat working that area saw the water in front of her go wrong. Discolored sea and then eruption at the surface. And then new land where the chart said there was open water. The boat was the Myojin Maru, number 11, and by the convention that lets the discoverer's name attached to the discovery, the feature became Myojin Sho, the shoal of the Myojin. Understand why that report landed the way it did in Tokyo. Japan in September 1952 had been a sovereign country again for less than 5 months. The occupation had formally ended in April, and the institutions that manage a maritime nation's own waters, the charting, the lights, the navigational warnings, the survey ships, were being rebuilt and restaffed and re-equipped under a young organization, the Maritime Safety Agency and its Hydrographic Office. A brand new island appearing in Japanese waters was not an academic curiosity to that organization. It was 3 separate obligations landing at once. The first was navigational. A shoal that was not on the chart yesterday and is on the surface today is a hazard to every vessel in the region, and it is the Hydrographic Office's specific legal job to find out where it is, how deep it is, and how big the danger area around it needs to be. Fishing fleets were working that ground. Somebody had to go and measure it. The second was scientific, and it was urgent in a way that is hard to reproduce today. Volcanology in 1952 had almost no direct observations of submarine eruptions. Nobody had been able to watch one closely. Here was one happening in Japanese waters, 400 kilometers from the capital, reachable by ship in about a day. Every volcanologist in the country understood that this was an opportunity that might not repeat in a career. The third was territorial, and it was not spoken about much, but it was real. New land above the waterline has legal consequences for a maritime state. Japan is a country whose national extent is defined by rocks in the ocean, and a country 5 months out of occupation had a strong institutional interest in knowing precisely what had just appeared inside its own waters. And there was a fourth pressure, the one that actually set the clock. The island was disappearing. That is not a figure of speech. These new cones are built out of loose fragmented volcanic material, ash and cinder and broken glassy rock, piled up by explosions. It has no strength. It is a heap. The moment it stops being fed and the ocean gets at it, it goes, and in a sea that runs the kind of swell this one runs, it can go in days. Through the second half of September 1952, observers watched the new island at Myojin Sho appear, grow, and be cut down repeatedly. By the 23rd of September, The land that had been reported 6 days earlier had eroded away entirely. The site was open water again. So the survey was not a matter of steaming out at leisure. It was a matter of getting there while there was still something to measure, and getting the depths recorded before the next episode changed them, and doing it in a window that might close at any moment. Anyone who has worked to a research deadline knows exactly what that pressure feels like. It is not recklessness. It is the entirely ordinary situation of a limited opportunity and a competent team who can see it closing. The ship assigned was the Kayomaru No. 5, a survey vessel operating for the Hydrographic Office. She sailed from Tokyo on the 23rd of September 1952 with 31 people aboard, her crew, and 9 scientists. Among the scientific party was a researcher named Ryoichi Mita, who is identified in Japanese accounts of the loss as having previously worked on the interpretation of the seafloor in that area. That detail is not decoration. It means the party going out to look at this thing included at least one person who had already thought hard about what was down there, which tells you the trip was not a stunt. It was the appropriate people doing the appropriate job. They also had reason to believe the immediate risk was low, and this is the part that has to be handled carefully. Because hindsight makes it look obvious, and it was not obvious at all. By the 23rd, the island was gone. Aerial observation of the site found it apparently quiet. Not smoking, not throwing material, not visibly erupting. To every instinct available in 1952, that reads as an eruption that has ended. The mountain built its cone, the cone was washed away, the show is over, and now somebody needs to go out and get the soundings before the weather turns. There was no seismic network capable of telling them otherwise. There were no gas measurements. There were no satellites. There was no monitoring buoy in the water. There was a look from an aircraft and a flat sea. And the whole interpretation rested on an assumption that seemed so reasonable nobody had reason to examine it. That a volcano which is not doing anything is a volcano that is not about to do anything. What nobody had yet established, because nobody had had the chance to study a shoaling submarine volcano properly, is that the physics here runs almost exactly backwards from intuition. Depth is what controls whether a submarine eruption is a gentle event or a bomb, and the relationship is not the one people expect. Take a volcano erupting on the deep sea floor, 2 or 3 kilometers down. The water above it is pressing on the vent at hundreds of atmospheres. At that pressure, water simply cannot do the thing that makes eruptions explosive, which is flash into steam and expand violently. Push water past a certain combination of pressure and temperature, and it stops behaving as a liquid that can boil at all. It becomes a dense supercritical fluid that carries heat away without the volume change. So a deep eruption is quiet. Lava comes out, chills into rounded pillow shapes, and stacks up. Ships pass overhead and notice nothing. Now bring the same vent upward. Every 100 meters of water you remove takes about 10 atmospheres off the lid. Somewhere in the last few hundred meters, the pressure falls low enough that seawater reaching hot magma can flash to steam, and steam occupies on the order of 1,000 times the volume of the water that made it. That expansion, happening inside and around molten rock, tears the magma apart into fine fragments, and the fragmentation exposes more hot surface to more water, which drives more steam, which drives more fragmentation. It is a runaway. The shallower the vent, the more violent it gets, right up until the cone actually builds high enough above the waterline to keep the sea out, at which point the eruption calms down again because the water can no longer reach the magma, which produces the ugliest fact in this entire story. The single most explosive condition a volcano in this arc can be in is the condition of being just below the surface. Not deep, not emerged, just below. And the depth band of maximum violence is exactly the depth band in which it makes and loses islands. and therefore exactly the depth band in which somebody reports a new island, and therefore exactly the depth band in which a hydrographic office is obliged to send a ship. The island vanishing on the 23rd was not evidence that the eruption had finished. It was evidence that the cone had been cut back down into the depth range where it was most dangerous. There is one more property that made the situation unreadable from the surface, and it is the reason no amount of care on the day would have helped much. These eruptions are not continuous. They pulse. A shallow phreatomagmatic vent can throw a column for a few minutes and then go completely silent for hours, because the process depends on water finding its way into a fracture system and then being blown back out, and that cycle can take as long as it takes. There are documented cases at this very shoal of eruptions minutes apart and then nothing for a day. A quiet surface tells you what the volcano is doing in that instant. It tells you nothing at all about the next one. So on the morning of the 24th of September 1952, the Kayo Maru No. 5 was working over a site that looked, by every observation available to human beings at that time, like a finished event. The sea was open. Nothing was showing. There were 31 people aboard, doing careful technical work. In the exact position where the most violent process this ark is capable of was loaded and waiting. At about 20 past 12, local time, the shoal went off underneath her. There is no eyewitness account of it. That is the first hard fact about the 24th of September 1952, and it constrains everything anyone can honestly say. No other vessel was close enough to watch. No distress transmission from the Kayo Maru No. 5 is documented. The ship was working over the site, and then the ship did not exist. And the interval between those two states cannot be reconstructed from anything anyone aboard did or said, because nothing anyone aboard did or said survived. What can be reconstructed is the physics, and the physics is brutally straightforward. Water does not compress. That single property is why an explosion underwater behaves nothing like an explosion in air. In air, a blast wave loses energy fast, and a structure some distance away gets pushed. In water, the energy couples directly into anything the water touches, and a hull sitting on the surface above a shallow vent is not being pushed sideways by a wave. It is being struck from below by an incompressible medium that has nowhere to go but up and outward, across the entire wetted area of the ship at once. There is no design of small survey vessel that survives that. On top of the shock, a shallow phreatomagmatic explosion throws solid material. Blocks of rock, some of it still hot, launched ballistically out of the vent and coming down across a wide area. There is also a third mechanism that gets less attention and matters more than people expect: gas. When a submarine vent releases a large volume of gas into the water column, the water above it becomes a froth, and froth is less dense than seawater. A ship floats because the water beneath her weighs enough to hold her up. Charge that water with gas, and the buoyancy under the hull falls away. A vessel sitting over a heavily degassing vent can lose the support that is keeping her on the surface. How much each of these three mechanisms contributed at Myojin Show cannot be separated after the fact. Any one of them, at that range, is sufficient. The evidence that came back said the rest. In the days that followed, search vessels and aircraft went out to the area and recovered debris, fragments of the ship. Pieces small enough to make the manner of destruction obvious without anyone having to speculate about it. And embedded in and adhering to that material was volcanic glass, the fine, sharp, glassy fragments that a phreatomagmatic explosion produces when magma is quenched and shattered by seawater. Analysis tied that glass to the material Myojin Show was erupting. That is the sentence that ends any argument. The Kayo Maru No. 5 did not founder in weather, and she did not strike an uncharted rock, and she did not vanish in a way that leaves room for interpretation. The seafloor came up through her, and the seafloor came back with the wreckage to prove it. 31 people were lost. 22 of them were the ship's company, and 9 were the scientific party. Ryoichi Mita, who had worked on the interpretation of that piece of sea floor, was among them, which means the volcano killed the man best placed to explain what it was doing. Now the part that reframes the whole event, and it happened 8,500 kilometers away in California, and nobody in Japan knew about it for a considerable time. Deep in the ocean, there is a layer, somewhere around 600 to 1,200 meters in most of the world, where the speed of sound reaches a minimum. Above it, warmer water speeds sound up. Below it, pressure speeds sound up. Sound that enters that layer at a shallow angle keeps getting bent back into it. So instead of spreading out in all directions and dying, it is trapped in a horizontal waveguide and travels for thousands of kilometers with remarkably little loss. It is called the Deep Sound Channel, or SOFAR, for sound fixing and ranging, and the United States Navy had built a network of hydrophone stations to exploit it. The original purpose was rescue. A downed aviator carried a small explosive charge, dropped it in the ocean, and shore stations thousands of kilometers apart timed the arrival of the sound and triangulated his position. 2 of those stations sat on the California coast, at Point Sur and at Point Arena. Across September 1952 and into the following year, they recorded a long series of sharp underwater explosions arriving from the far side of the Pacific. The analysis was published in 1954 by Robert Dietz and E.J. Sheehy, and what they showed is that the Myojin-sho eruptions had been detected, timed, and located by underwater sound from roughly 8,600 kilometers away. The volcano that destroyed a Japanese survey ship was audible in California. Closer in, at Hachijojima, about 130 kilometers north, a tide gauge recorded the water moving. An instrument sitting in a harbor on a populated island wrote down the event in ink while it was happening. So the world's instrumentation registered the death of that ship on 2 continents worth of sensors, and not one of those recordings did the slightest good to anyone aboard. The California stations were listening for a completely different signal, on a different circuit, in a different navy, and the interpretation came out in a scientific journal 2 years later. The Hachijojima gauge was a tide gauge. It measured. It did not warn anyone because there was no system that turned a measurement into a warning, and even if there had been, the ship was already gone by the time the water arrived. That gap between what can be detected and what can be acted on is the single most persistent feature of this region across the entire century this story covers. Detection improved enormously. It kept improving, and it is still in 2023 running behind the events by margins measured in days. There is a cruel, practical footnote to the search itself. Anyone going out to look for the Kaiomaru No. 5 was going out to a vent that had just destroyed a ship and had not stopped. Myojin-sho kept erupting. It went through 1952 and into 1953, and it came back in the years after that, building cones and losing them, throwing material, discoloring the sea. The searchers were working a hazard area whose exact boundary nobody could define, because the boundary depended on how big the next explosion was, and nobody could predict the next explosion. This was not a case of rescuers arriving to a settled scene. The scene was still live and stayed live for months. Japan's response was the correct one, and also an admission. A danger zone was declared around Myojin-sho, and the way that piece of ocean is studied was permanently changed. You do not put a manned ship over an active submarine vent to take soundings. You look from the air. You keep standoff distance. You accept worse data in exchange for people who come home. In the decades since, the Japan Coast Guard's Hydrographic and Oceanographic Department has built its submarine volcano surveillance around aerial survey and, more recently, small unmanned surface craft that can be sent into water no crew should be in. That change addressed one specific thing exactly, and left another completely untouched. It removed government surveyors from the top of erupting vents. It did nothing whatsoever about the fishing fleets, the ferries, the transport aircraft, and the merchant traffic that continue to cross this region every day and have no way of knowing which patch of empty blue water has a loaded vent under it. And there is a question the 1952 case answers so cleanly that it is easy to miss how strange the answer is. Why was a quiet volcano lethal? Because quiet is a description of the surface, and the surface is the least informative part of the system. The vent was not dormant. It was between pulses, at the shallowest and most dangerous depth it had occupied in its recorded existence, having just demonstrated that depth by building an island and then losing it. Everything the Hydrographic Office observed on the 23rd of September was true. The island had eroded. The site looked calm. The aircraft saw nothing. All of it accurate and all of it useless, because the information that mattered was under the water, and there was no instrument in existence that would have shown it to them. That is an uncomfortable conclusion, and it should be. 31 competent people, working for a professional organization, doing legally required work, with the best available observations, made a decision that any reasonable person in 1952 would have made, and the decision was fatal. Not because they were careless, because the category of information they needed did not exist yet. Which brings up the thing that has been sitting underneath this story since the feather settlement on Torishima, and which is about to become the center of it. At Torishima in 1902, there were no witnesses, but there was an island afterward, and geologists could read what had happened in the rock. At Myojin-sho in 1952, there were no witnesses, but there was wreckage, and chemistry proved the cause. In both cases, the hazard erased the people and left the evidence. 5 years later, off the same chain of islands, something took a large 4-engine aircraft with 67 people aboard and left nothing at all. No wreckage, no signal, no cause. And into that particular kind of nothing, an entire mythology was about to be poured. On the 22nd of March 1957, a United States Air Force C-97 Stratofreighter, serial 50-0702, left Wake Island for Yokota, in Japan. There were 67 people aboard, a mix of crew and passengers on a routine transport run across the Western Pacific, the kind of flight that happened constantly in that decade and almost always ended with wheels on concrete and people queuing for a bus. The aircraft was flying on instruments at 8,000 feet. Conditions along the route included cloud, turbulence, and reported icing. It made a routine position report. Nothing after that. No distress call. No emergency transmission. No further contact of any kind. The search that followed ran for 8 days and involved aircraft and surface vessels across an enormous stretch of open ocean, and it found nothing. Not a piece of wreckage. Not a slick. Not a seat cushion. The official cause of the loss is undetermined, and it has remained undetermined ever since. Now that word matters, and it gets abused constantly by people with books to sell. Undetermined does not mean unexplainable. It means the evidence required to choose between candidate explanations was never recovered. Those are completely different statements, and the distance between them is where an entire industry of nonsense set up shop. So look at the candidates, because they are neither exotic nor short of precedent. The C-97 was a big piston aircraft developed out of the B-29 lineage, powered by 4 Pratt & Whitney R-4360 radials. The R-4360 is one of the most complicated reciprocating engines ever put into production, 28 cylinders arranged in 4 rows, an engineering achievement and a maintenance burden, and the type had a well-documented history across many airframes of engine failures and engine fires. A fire in a nacelle over open ocean at night in cloud is not a mystery. It is a known way to lose a large aircraft. Icing is the second candidate. And at 8,000 feet in cloud in March, it is a real one. Structural ice does several things at once, none of them helpful. It adds weight. It changes the shape of the wing, which is not a cosmetic issue, because the wing's ability to make lift depends entirely on that shape, and a rough accreted leading edge can raise the speed at which the wing stops flying by a substantial margin. It builds on propeller blades, where it throws the balance off and shakes the engine mounts, and where it sheds unevenly and asymmetrically. It builds on the airframe faster than de-icing systems designed for a different era can clear it. Aircraft have been lost to ice in every decade since aviation began, including recent ones with far better protection than a 1957 transport had. Turbulence is the third. Severe turbulence in this specific region is not a footnote. Remember what is going on in the atmosphere over the Kuroshio in the cold months. Warm ocean, cold air off the continent, enormous energy transfer, rapid cyclogenesis, and the jet stream over Japan in winter and early spring is among the strongest anywhere on Earth. Air moving at those speeds over a mountainous archipelago and across sharp temperature gradients produces clear air turbulence and mountain wave activity that can be violent and, in 1957, entirely undetectable in advance. Any one of those, or a combination, will take an aircraft down. None of them requires anything unusual, and the reason none of them can be confirmed is not that the ocean is strange. It is that the ocean is deep and it moves. Here is the arithmetic that people who write about vanishing aircraft never do. An aeroplane that strikes water at speed does not sink as an aeroplane. It comes apart. The heavy structure, engines, spars, landing gear, goes down immediately, and along this line of ocean, it goes down into water that can be 4, 5, 7, 9,000 meters deep. In 1957, there was no technology on Earth that could have recovered anything from that depth, and there is very little now that could find it without knowing the location to within a few kilometers, which nobody does. What is left floating afterward is a small quantity of light material, cushions, insulation, some fuel and oil on the surface, personal items. And that material does not stay where the aircraft hit. It sits in the Kuroshio, or in the eddies that spin off it, and moves at 3 or 4 knots. Do the multiplication. 3.5 knots is roughly 84 nautical miles a day. If the search does not reach the right patch of water within 24 hours, and it did not, because nobody knew where the right patch of water was, the debris is 150 or 200 miles downstream and spreading, in a sea state that hides small floating objects in the troughs. And nobody knew where to look for a reason that is not a failure of anyone's competence. Over-ocean navigation in 1957 was celestial fixes when there were stars, dead reckoning between them, radio bearings when a station was in range, and a position report passed by high-frequency radio at intervals. A position report is a best estimate. A best estimate can be off by tens of miles in strong upper winds, and the upper winds over Japan in March are among the strongest in the world. So the search does not begin at a point. It begins at a smear, and the smear is drifting. Work through what a search of that kind actually is. An aircraft flying a search pattern at 1,000 feet with good visibility can effectively sweep a corridor perhaps 15 or 20 miles wide, and it does so at a couple of hundred knots, and it can stay out for a limited number of hours before it has to go home and refuel. On the best possible day, one aircraft covers a few thousand square miles. Put 20 aircraft up and you cover more, at the cost of coordination, overlapping tracks, and gaps. And the area of uncertainty, once you allow for a drifting debris field and an uncertain starting point, runs into the tens of thousands of square miles and grows every day you search. The people flying it are doing the least glamorous work in aviation. An ocean search is hours of straight and level at low altitude with observers pressed to scanning windows, and human visual search degrades quickly, which is why crews rotate observers on a clock, rather than trusting anybody to stay sharp. Everything below is the same color. Every whitecap is a shape that might be something and is not. Air crews come back after 10 or 12 hours, having seen an empty sea, refuel, sleep badly, and go out again over a different rectangle, knowing that the rectangle they flew yesterday has since drifted somewhere they are no longer looking. 8 days of that produced nothing, which, given the numbers, is not shocking at all. It is the expected outcome. There is a version of this story where that ending is dissatisfying, and the dissatisfaction gets converted into something else. That is what happened. 67 people went into the Pacific and left no trace. And because there was no trace, there was no story. And because there was no story, other people wrote one. Understand precisely what the raw material was, because the mundane version is more interesting than the invented one. Across the late 1940s and early 1950s, Japan lost fishing vessels in the waters south of Tokyo. Not a handful of great ships. Small boats mostly, working the grounds we have already described, in a period when the fleet had been rebuilt fast and hard out of post-war necessity, when many hulls were wooden and under 100 tons, when radio was inconsistent, and when the economic pressure to be out on the water was severe. Some were lost in bad weather. Some were lost near an erupting shoal that the authorities had, correctly, declared dangerous. Some were simply never explained, because a small boat that goes down 200 miles offshore with no radio call leaves the same amount of evidence as a large aircraft, none. Those losses were spread across roughly 5 years, and across a stretch of ocean about 1,200 kilometers long, running from Miyakojima all the way south to Iwo Jima. 1,200 kilometers is the distance from London to Rome. Scattered across a span like that, over 5 years, in the most worked fishing grounds in the region, in a sea with the wind and current behavior we have already gone through, those losses are a maritime safety problem. They are not an anomaly. They are the ordinary, grinding cost of a dangerous industry, and every fishing nation on Earth has a version of the same ledger. And the Japanese government's actual response tells you exactly how they understood it. They did not declare a triangle. They did not designate an enormous region of ocean as cursed water. They declared a danger area, and it was a small radius around one specific erupting shoal called Myojin-sho, because that is where the specific, identified physical hazard was. Then a writer in the United States got hold of it. Charles Berlitz published The Bermuda Triangle in 1974, and it sold in numbers most authors will never see. In it, and in the material that followed through the 70s and after, he presented a Pacific counterpart to his Atlantic mystery, and the Japanese waters south of Tokyo were pressed into service as the Devil's Sea. The claims were specific enough to sound researched. 9 ships had vanished there between 1950 and 1954, he said, without trace and without explanation. The Japanese government had responded by declaring the region a danger zone, and it had sent out a research vessel carrying more than 100 scientists to investigate, and that vessel had disappeared inexplicably, adding its crew to the toll. Every element of that is either false or so distorted that the truth is unrecognizable inside it, and the man who established that did it the boring way, with a filing cabinet. Lawrence Couchet was a research librarian at Arizona State University and a flight instructor, which turns out to be an unusually well-suited combination for this problem, because half the legend concerned aircraft and half of it concerned archives. He got so many requests from students for material on the Bermuda Triangle that he started checking the sources himself. What he found was that the original newspaper reports, the contemporary weather records, the Lloyd's listings, and the official investigations frequently said something completely different from what the popular books said. Storms that had been raging on the day were left out. Ships described as vanishing without trace had been found. Some incidents had never happened at all. He published The Bermuda Triangle Mystery, solved in 1975, and described what he had found as a manufactured mystery, built on misconceptions, poor reasoning, and sensationalism, and repeated by writers who did not check. On the Devil's Sea specifically, he wrote to Japanese authorities and went to the sources, and the answers came back flat. The vessel with 100 scientists aboard was the Kaio Maru number 5. She had 31 people aboard, not more than 100. She did not disappear inexplicably. She was destroyed by a volcano that was in eruption, that had been reported in eruption a week earlier by a fishing boat, that had built and lost an island in the days beforehand, and that had been detected exploding by underwater sound stations on the far side of the Pacific Ocean. Wreckage was recovered. The volcanic glass in it was analyzed. The cause of loss is one of the better documented maritime destructions of the mid-century. The 9 mysteriously vanished ships were small fishing boats, several of them poorly equipped for radio, lost across 5 years, and the entire length of that stretch of ocean, frequently in bad weather. And the danger zone the Japanese government declared was not a triangle spanning a third of the western Pacific. It was a small circle drawn around one shoal because one shoal was what had gone off. Kushi was right. That should be said clearly and without qualification, because it is not a close call and there is no interesting counter-argument. He did the work held up, and the popular version was garbage. And here is where this story turns in a direction that almost nobody follows it in. Being right had a cost. When the mystery collapsed, the ocean collapsed with it. The Devil's Sea got filed, in the general public mind, and in a lot of journalism since under-debunked, and debunked is a very strong word. It does not mean the specific claims were false. In practice, it means nothing to see here. So a stretch of ocean, with a documented history of destroying vessels, an active volcanic arc with dozens of shallow vents that produce and destroy islands on a scale of days, a current that removes evidence at 80 miles a day, and a rescue geometry that leaves crews a full day from meaningful help, got mentally reclassified as a place where nothing unusual happens, because a best-selling author had invented the version everyone remembers. Both of those framings are wrong, and the second one is the more expensive. The invented mystery buried the real one. Berlitz took 31 people who were killed by an identified volcanic explosion while doing their government's work and converted them into 100 fictional victims of nothing in particular. And in the process, he erased the actual mechanism that killed them. Then the correction erased the mechanism a second time, by association. Because once a subject is a punchline, it stops being examined. The strange part, and the part that ought to bother anyone, is that the true hazard is far more repeatable than the fake one. Ghost ships and vanishing aircraft do not come back on a schedule. Submarine volcanoes do. This arc has produced destructive events in 1902, in 1952, in 1986, in 2000, in 2021, and in 2023, along with a long list of eruptions that did not happen to have anyone standing on top of them. A curse would have been better news. A curse is not on a timetable. So what does the modern era actually bring to this problem? Quite a lot, and it deserves precision because dismissing modern capability is as lazy as trusting it blindly. Position is solved. A vessel today knows where she is to within a few meters, continuously, and larger ships broadcast that position automatically to anyone with a receiver. The problem that made the 1957 search a smear on a chart instead of a point does not exist in the same form. Distress alerting is solved, or nearly. Since the 1980s, a satellite system has existed specifically to hear emergency beacons. A modern beacon transmits on a dedicated frequency, is picked up by satellites, and delivers an identity and, in current units, a position accurate to 100 meters or so, anywhere on Earth, with no need for anyone to be listening on the right channel at the right hour. The entire scenario of a boat quietly failing to come back, which killed people up and down this chain for a century, has a technical answer now. Weather is transformed. Japan operates geostationary satellites that image the whole visible hemisphere every 10 minutes, and the area around Japan far more often than that, so a developing system is not a surprise, and a volcanic plume is visible in near real time from space. Earthquake response is genuinely the best in the world. Japan's seismic network is dense and fast, and the meteorological agency can issue a tsunami warning within about 3 minutes of a large offshore earthquake, which is an extraordinary institutional achievement built out of a very painful history. Now the limits, because every one of those capabilities has a boundary, and the boundaries are where people still die. A beacon shortens the time to being heard. It does not shorten the distance to the nearest ship or aircraft. And along this island chain, those distances are hundreds of kilometers. A perfect position report from 400 kilometers out is a perfect position report that help will reach in most of a day. Satellite imagery shows a plume above the water. It shows nothing below it. The most dangerous condition a volcano in this arc can be in, the one that killed the Kayo Maru No. 5, produces no plume at all until the moment it does. Seismic warning depends on the earthquake being the right size for the wave. Hold that sentence, because it is about to matter enormously. And the dense instrumentation, the seafloor observatories that Japan has invested in so heavily, sits where the threat to the mainland sits, off Tohoku and along the Nankai Trough. It does not run down the volcanic arc into the deep Pacific. The volcanoes that receive continuous, close, instrumental attention are overwhelmingly the ones near populations. 600, 1,000, 1,300 kilometers south of Tokyo. The monitoring thins out to periodic aircraft flights and whatever a satellite happens to catch. There is one more effect, and it is the one modern operators consistently underrate. Better capability does not simply make the same activity safer. It expands the activity. Better forecasting extends the working season. Better navigation opens routes that were previously avoided. Better engines carry a fishing boat further from port. Better communication makes owners and schedulers comfortable sending vessels to places they would have hesitated over. The safety margin does not get banked. It gets spent on range, on season length, on traffic, on economics, and the result is more people in more places at more times of year, still bounded by exactly the same physical constraints when something goes wrong. Before following that expansion out into the deep water, it is worth looking at the two occasions in living memory when this arc went off directly underneath a population, close to Tokyo, with all of that modern capability switched on and pointed at it. Because those are the cases where the system worked. They are also the cases that show precisely what the system is made of, and how narrow the conditions are that let it work at all. Izu Oshima is the first island in the chain, about 120 kilometers south of Tokyo, close enough that on a clear day you can pick it out from the beaches of the Izu Peninsula. It is a single basaltic volcano called Miharayama, with a town around its skirts, and it erupts often, roughly every few decades, usually in a way that draws tourists rather than emergency services. Basaltic lava is runny and comparatively well-behaved. In the past, eruptions there had been an attraction. People took the ferry out to look at the glow. In mid-November 1986, it started again at the summit, and for the first week, it behaved exactly as expected. Fire fountains inside the central crater, spectacular at night, contained within a caldera that had held every previous episode. Sightseeing boats and aircraft went out. Roughly 10,000 people lived on the island, and they had lived with this mountain their whole lives. And there was no particular reason on the 15th of November to think this one was different. On the 21st, it opened outside the crater. A fissure tore across the caldera floor, and then out onto the outer flank of the volcano, on the side facing the main town of Motomachi, and started producing lava fountains hundreds of meters high along a line, feeding flows that began moving downhill toward the settlement. That is a different event from a summit eruption in the way that a fire in a fireplace is different from a fire in the hallway. The containing structure was no longer containing anything. The decision was made that evening to take everybody off the island. Consider what that actually required. 10,000 residents, plus visitors, plus the practical problem that a volcano throwing lava at your only town is also throwing it at your roads. The evacuation was run through the harbors at night, using every hull that could be brought to bear. The regular ferries, Japan Coast Guard vessels, ships of the Maritime Self-Defense Force, and local fishing boats belonging to the people being evacuated. Over the course of that night and the following morning, essentially the entire population of Izu Oshima was moved off the island and landed at Tokyo and other ports. Nobody died. That is the single most important sentence in this entire story, and it is easy to skate past because nothing bad happened. 10,000 people were removed from an erupting volcano in one night, by sea, in the dark, and the death toll was 0. Set that beside Aogashima in 1785, where roughly half the population of an island of 327 people did not get off. Same island chain, same class of volcano, same fundamental problem of an island where the only exit is a boat. The difference is not courage, and it is not competence, because the people of Aogashima in 1785 had plenty of both. The difference is 4 specific, boring, physical things. Izu Oshima has harbors, and Aogashima does not. Izu Oshima is 120 kilometers from the largest concentration of ships in Japan, and Aogashima is over 350 kilometers from anywhere with a fleet. Izu Oshima was instrumented and watched, so the shift from summit activity to flank activity was seen and understood almost immediately, and Aogashima in 1785 had nothing but the evidence of people's own senses. And on the night of the 21st of November 1986, the sea was workable. That last one is not a small caveat, and it should not be tucked away. If that night had brought a northerly against the current, and a 3-meter swell breaking on the harbor entrances, the evacuation of Izu Oshima would have been a very different event, and there was no alternative plan, because there is never an alternative plan on an island. The operation succeeded on the weather as much as on the organization. The residents were away for about a month. The evacuation order was lifted before the end of December, and they went home to a town that the lava had not reached, and Izu Oshima has been inhabited ever since. In the shadow of a volcano everyone knows will do it again. 14 years later, 60 kilometers further south, the same chain produced a case that no evacuation plan in the world was designed for, because the hazard did not destroy anything at all. Miyakejima is another basaltic island volcano, another few thousand people, and another mountain with a habit. It had erupted in 1940, in 1962, and in 1983, so roughly every 20 years. And by 2000 the island was, in the most literal sense, due. It began in late June 2000, and at first the concern was the usual one: magma moving, and the possibility of an eruption breaking out somewhere inconvenient. Then in July the summit did something unusual. It collapsed. The floor of the crater subsided and kept subsiding, and over the following weeks, a caldera roughly 1.5 kilometers across opened at the top of the island, which means an enormous volume of rock dropped downward into space that the magma had vacated underneath it. There were explosive eruptions and ash falls in August, and heavy rain on fresh ash produced mud flows, which is a standard and dangerous combination. None of that is what emptied the island. What emptied the island was sulfur dioxide. The system that opened up beneath Miyakejima began venting gas continuously, at rates that put it among the largest sustained volcanic gas emitters ever measured, on the order of tens of thousands of tons a day at the peak. Sulfur dioxide is not exotic, and it is not slow. In sufficient concentration, it attacks the airways directly, and the people most at risk are the ones with asthma, the elderly, and children, which is to say a substantial fraction of any island community. On the 1st of September 2000, the order went out, and over the following days, the entire population, roughly 3,800 people, left the island. They did not come back for 4 years and 5 months. The evacuation order was lifted on the 1st of February 2005. Found 5. Think about what 4.5 years does to a community of that size. Businesses that had customers do not have customers. Fishing boats tied up elsewhere. Children who left primary school on Miyakojima and finished secondary school in Tokyo, with their friendships and their expectations and their entire sense of where home is rebuilt somewhere else. Houses standing empty through 4.5 years of salt air and typhoons. Elderly residents who died in temporary accommodation on the mainland without seeing the island again. And here is the detail that captures the whole thing. The reason they could not return was not that the island was destroyed. Most of it was not. The houses were largely standing. The roads were there. The harbor worked. The island was intact and unbreathable, which is a category of disaster that most people have no mental slot for, and which no amount of construction or reinforcement addresses, because you cannot armor a lung. When they did return, they returned carrying gas masks. That was a condition of going home. Detection equipment was installed across the island, alarm systems set up, areas of higher concentration kept restricted, and people with respiratory conditions were advised that returning was not safe for them. Residents went about ordinary daily life with a mask within reach for years, on an island whose mountain was still exhaling. Not everybody went back. The population has never recovered its former number. Set the two cases side by side, and the shape of the modern system is fully visible. Izu Oshima proves that when a volcano is close, watched, harbored, and reachable, a modern state can take 10,000 people off it in a night and lose nobody. Miyakojima proves that even a complete success in that sense can cost a community half a decade of its existence, and that the hazard does not have to knock anything down to win. Both islands are within a couple of 100 kilometers of Tokyo. Both are permanently instrumented, both have ports. Both are inside the reach of ships and helicopters that can be there in hours. Now take that same volcanic arc and run it south, past Hachijojima, where the airport is, past Aogashima and its cliff face landing, past the Bayonnaise Rocks, past Torishima, where nobody has lived since 1965, past Sofugan, which is 100 meters of bare stone in open ocean, out to where there are no residents to evacuate, no harbors to evacuate them through, no instruments on the vents, and no ships within a day's steaming. And out there, in the autumn of 2021, hundreds of modern vessels with satellite navigation, radio, radar, and thoroughly reliable diesel engines were disabled and damaged by a volcano they never saw, which had stopped erupting 2 months earlier, more than 1,000 kilometers away, 1,300 kilometers south of Tokyo, 5 kilometers north of an uninhabited island called Minami Iwo Jima. There is a submarine volcano with a name that translates roughly as the shoal of the fortunate virtue, Fukutoku Oka no Ba. For most of the 20th century, its summit sat around 25 to 30 meters beneath the surface, which is to say it spent decades parked in precisely the depth band that the Kaio Maru No. 5 was destroyed in. It has a track record, and the track record is the same story told 4 times. In 1904, it erupted and built an island, and the island washed away. In 1914, it erupted and built an island substantial enough to be named, and within about a year, the sea had taken that one too. In 1986, it erupted again, threw up a cone roughly 600 meters long, and the ocean removed it in a couple of months. There was activity again in 2005 and in 2010. Discolored water and disturbed sea, the standard signature of event working below the surface. 4 island-building episodes in a century, and 4 demolitions all at the same spot, all recorded, all publicly known, which means that by 2021 the Japanese state understood this specific volcano extremely well as a geological object. What nobody had ever had to deal with was what it would do if it went properly. On the 13th of August 2021, it went properly. The eruption was seen immediately, and that is worth pausing on, because it is the single clearest measure of how much changed between 1952 and now. Japan operates geostationary altimeter weather satellites that photograph the entire visible face of the planet every 10 minutes, and the region around Japan far more frequently. When Fukutoku Okanoba erupted, the column appeared in satellite imagery in near real time, and the scale of it was not ambiguous. The plume punched up to roughly 16 kilometers, straight through the top of the weather layer and into the stratosphere, and spread out into the flat anvil shape that only very energetic columns produce. Aircraft could see it from a long way off. It was reported as the largest eruption in Japan by volume since Sakurajima in 1914. It built an island again, a horseshoe of fresh volcanic debris, around a kilometer across, curved around the vent, and photographs of it from Coast Guard aircraft in the following weeks show exactly what these things are. A gray heap of loose, fragmented rock sitting in blue water, with waves already eating the edges. It began disintegrating almost at once, and by the following year, the ocean had done what it did in 1904 and 1914 and 1986. Nobody was killed. Nobody was injured. There were no settlements to destroy, no survey ship on top of it, no fishing fleet in the immediate danger area. On the day, in the place, this eruption was a spectacular natural event with a human cost of zero. The damage started 7 weeks later, 1,300 kilometers to the west, and it went on for months. To understand why, you have to understand what the volcano actually produced, because the plume was the smallest part of it in terms of consequence. When magma at 1,000 degrees or more decompresses quickly, the gas dissolved in it comes out of solution the way carbon dioxide comes out of a shaken bottle, except that the liquid it is escaping from is molten rock, and molten rock is viscous enough that the bubbles cannot get out. So the melt foams. It expands into a froth of glass walls around trapped gas cavities, and then it is quenched, and the froth freezes in place. The result is pumice, a rock that is mostly holes. Its bulk density can fall to a third or a half that of water. Drop it in the sea, and it floats, and it keeps floating, sometimes for months, sometimes for years, until enough water works its way into the connected pore spaces to bring it down. Fukutoku Okanoba produced this material in a quantity that does not translate easily into words. The rafts observed near the volcano in the days after the eruption covered on the order of 100 square kilometers of sea surface. A pumice raft is one of the stranger sights in the natural world, and every crew who has run into one describes the same thing. The water stops behaving like water. A raft is not a solid sheet. It is a dense, loose slick of floating gravel and cobbles, sometimes tens of centimeters thick, and it damps wave motion so effectively that the surface goes flat and gray, and slightly matte like wet concrete out to the horizon. Boats push through it, leaving a trail that closes behind them. In the dark, and out of the corner of a radar screen, it looks like nothing at all, and it moves. Not with the wind particularly, but with the water. And the water in this part of the Pacific moves in very specific directions that have been mapped for a century. The pumice from Fukutoku Okanoba went west. It was picked up by the broad westward flow of the tropical North Pacific and carried slowly and without any drama at all across open ocean toward the Ryukyu Islands. It took about 50 days to cover the first 1,000 kilometers. On the 4th of October 2021, it arrived at Kitadaido and Minamidaido, two small isolated islands east of Okinawa, with fewer than 2,000 people between them. Between the 11th and the 14th of October, it reached Amami and Okinawa itself. Now count what that means. An eruption that occurred on the 13th of August at a spot in the ocean 1,300 kilometers away, with a human cost of exactly zero on the day, began doing serious economic damage to inhabited islands in the second week of October. 2 months later, the volcano had been finished for weeks. The hazard had not. Nobody in the Ryukyus watched that column go up in August, and understood that they had 7 weeks. The connection between the eruption and what was drifting toward them existed, in the sense that the science of pumice rafting is well established and drift models exist and specialists were aware of the material. But the practical experience of it, for a harbor master on Okinawa or a fishing cooperative on Kitadaido, was not a warning followed by an arrival. It was an arrival. Count that as the 3rd distinct failure mode this ocean has produced in 120 years, and it belongs beside the others. Torishima in 1902 was a hazard that killed everyone present and left no account. Myojin-sho in 1952 was a hazard that was invisible until the instant it was fatal. Fukutoku Okinoba in 2021 was a hazard that was seen perfectly in high resolution from space in real time by everybody, and still arrived unannounced because what mattered was not the part anyone was looking at. The people who found out first were the ones with the smallest margins. The Daido Islands sit alone in deep water more than 300 kilometers east of Okinawa. They have no natural harbors worth the word, and their supply, like Ogasawara's, is a ship. When floating rock fills the approaches to a port like that, the ship does not come in, and the island does not get resupplied. And there is no alternative route because there was never an alternative route. And then the boats started stopping. Every diesel engine in every boat in that region is cooled by the sea. Not metaphorically. There is a hole in the hull below the waterline, covered by a grating, leading to a valve, leading to a basket strainer, leading to a pump, and that pump pulls seawater through the engine or through a heat exchanger and pushes it back out through the exhaust. The strainer basket exists to catch seaweed and plastic bags. It is a mesh cage, roughly the size of a coffee tin on a small boat. Pumice gravel packs that cage solid in minutes. What follows is fast, and it is not survivable for the machinery. On a small vessel, the raw water pump usually has a rubber impeller, and that impeller relies on the water going through it for both lubrication and cooling. Cut the flow, and the vanes tear themselves apart almost immediately. Engine temperature climbs. On many boats, the exhaust system is itself cooled by that same seawater, injected into the exhaust to keep the rubber hose from burning. So losing raw water can set the exhaust line alight or fill the cabin with fumes. The alarm goes off. The only correct action is to shut the engine down at once, and then the boat is adrift in a raft of floating rock, with the propulsion system that was supposed to get her home now a hot lump of metal. Clearing it is possible, and it is nearly pointless. You close the seacock, open the strainer housing, dig the gravel out with your hands, close it up, open the valve, bleed the air, restart. Perhaps 10 or 15 minutes if everything goes well and the sea is kind. And then you are still sitting in the pumice, and the strainer starts filling again from the moment the pump turns. Crews who tried this reported doing it repeatedly and getting nowhere, because the problem is not a blockage. The problem is the water itself. Bigger ships did better and not by as much as anyone expected. A large vessel has a proper sea chest with a coarse grating and duplex strainers that can be switched over and cleaned while running, which buys time. It does not buy immunity, and pumice is volcanic glass, which means it is abrasive, and it scours pump faces and shaft seals and anything else it travels through. Craft with water jet propulsion, which have become common for fast ferries and patrol boats, fared worst of all because a jet drive's entire operating principle is swallowing the water it is sitting in. So across October and November of 2010, the fleets of the southwestern islands did the only thing available. They stopped. Hundreds of vessels were reported damaged. Fishing boats stayed tied up because going out meant a repair bill larger than any possible catch and a real chance of being disabled offshore. Ferry services to the smaller islands were suspended, and that is not an inconvenience in the Ryukyus, it is a supply cut. Islands like Kume, Iheya, Izena, Aguni, and the 2 Daido Islands run on a boat. The boat brings the food that is not grown there, the fuel, the mail, the construction materials, the parts, and it takes people to hospital appointments on the main island and children to schools and examinations. When it stops, none of that has an alternative, because none of those islands has an airport capable of replacing a cargo ship, and several have no useful airstrip at all. The harbors themselves filled up. Pumice does what any floating debris does. It goes where the wind and the water put it. And what the wind and water do to a bay is pack the floating material into the corners and against the keys. Ports across Okinawa and Kagoshima prefectures ended up with basins carpeted in gray rock, in places deep enough to walk on, which people did and photographed, and which does not make it any easier to get a boat out. The figures that came out of the cleanup are the useful measure of the whole thing. 71 harbors affected. Costs in Okinawa reported above 515 million yen. More than 110,000 cubic meters of pumice removed. That last number deserves to be turned into something you can see. 110,000 cubic meters is a solid cube, roughly 48 meters on every side. It is on the order of 11,000 full dump truck loads of rock, lifted out of the water, moved, and disposed of by excavators and dredgers and nets and boom lines and people with shovels over months, while more of it kept arriving on the current. It is not a cleanup in the sense of a single operation. It is a season of work, and the material was still coming in while the earlier material was being carted away. Now here is the reversal in this incident, and it is not rhetorical, it is mechanical, and it should make anyone who works on boats uncomfortable. Take a sailing vessel from the 1850s, the sort of hull that was working these waters when Manjiro was picked up off Torishima, and drive it into a pumice raft. What happens? The hull gets scratched. The rudder might collect some debris. Progress slows in the damped water. She sails on. There is no seawater intake because there is no engine, because the propulsion system is a piece of canvas attached to the sky. Take any modern vessel in Okinawa in October 2021 and put it in the same raft, and it stops within minutes. Every single improvement in marine propulsion over the last 150 years, all the reliability, all the power, all the range, all the independence from wind, is built on the same non-negotiable requirement: a continuous flow of seawater through an opening the size of a fist. That requirement is invisible in normal operation. Nobody thinks about it. It is the most reliable thing on the boat, and it is a single point of failure that a volcano 1,300 kilometers away can activate remotely, at scale, across an entire archipelago, 2 months after it has stopped erupting. The modern fleet was not better protected against this than a 19th century fleet. It was worse. That is not a comfortable finding, and there is no way to argue around it. There is a second-order effect from all this that got very little attention and matters more than the harbor cleanup bills. When the boats stop, the search and rescue capability of a region stops with them. In coastal Japan, as everywhere else, the practical first responders to a vessel in trouble are other vessels. The fishing boat 2 miles away that hears a call and turns. When the entire local fleet is either tied up or disabled, that layer is gone, and everything falls back on the Coast Guard, whose vessels were transiting the same water and dealing with the same intakes. The response network in an emergency is made of the same machines the hazard disables. Nobody plans for that, because nobody imagines a hazard that turns off engines. The pumice did not stop at Okinawa. It kept going, and where it went next closes a circle that has been open since the beginning of this story. Once the rafts reached the waters around the Ryukyus, some of that material got caught in the Kuroshio, and the Kuroshio does one thing. It runs northeast along the southern face of Japan. Through late November and into December 2021, pumice from Fukutoku Okinoba began appearing on the Izu Islands, along the coasts of Shizuoka and Kanagawa and Chiba, and inside Tokyo Bay. Boats in Sagami Bay had the same fouled strainers that boats in Okinawa had. Marinas within sight of the capital were skimming gray gravel off the surface. Follow that path on a map, because it is genuinely absurd. The volcano is 1,300 kilometers due south of Tokyo. Its debris traveled roughly 1,300 kilometers west to the Ryukyus, then turned and traveled well over 1,000 kilometers northeast up the length of Japan, and arrived in Tokyo's own harbor about 4 months after the eruption. It took the long way home, and the thing that carried it is the same current that made this region's fishing grounds rich, the same current that steepens the winter seas into breaking walls, and the same current that took a 14-year-old off the coast of Shikoku in 1841 and delivered him to the cone that 61 years later killed every person who settled on it. The Kuroshio is not an incidental feature of this story. It is the circulatory system. It is what makes the region worth working, what makes the weather in it violent, what erases the evidence when something is lost, and what distributes the consequences of an eruption across 2,500 kilometers of coastline belonging to people who never saw it happen. And by the time that pumice was washing up on the Kanto coast, something had already occurred on the other side of the Pacific that dismantled the last comfortable assumption anyone had about warning systems. On the 15th of January 2022, the submarine volcano Hunga Tonga Hunga Ha'apai erupted in the South Pacific. It is a different ocean and a different subduction system from the Izu Ogasawara Arc, so nothing here is a claim about the same volcano. But it is exactly the same class of source, a shallow submarine vent doing what shallow submarine vents do, at a scale that had not been observed with modern instruments before. The column went up to something like 57 kilometers into the mesosphere, higher than any eruption plume ever measured. The blast generated a pressure wave in the atmosphere that traveled outward around the entire planet and was recorded on barometers on every continent several times over as it circled. Japan is roughly 8,000 kilometers from Tonga. In the early hours of the 16th, Japanese tide gauges started rising, and they started rising earlier than any tsunami model said they should, and higher, because a substantial part of what reached Japan was not an ordinary ocean wave at all. It was water being driven by that atmospheric pressure wave, which moves at the speed of sound in air and therefore outruns a tsunami traveling through the ocean. The meteorological agency had to make a decision in the middle of the night about a phenomenon its entire warning architecture was not built for. It issued tsunami warnings and advisories along the Pacific coast, hours after an eruption, on the basis of water that was already arriving. Sea level rises of well over a meter were observed, with figures around 1.3 meters reported at Amami and comparable values on the Tohoku coast. Something on the order of 230,000 people were advised to evacuate in the dark in January for a wave produced by a volcano nobody in Japan had felt, seen, or heard. The agency was candid afterward that this did not fit the framework, and it changed the framework, saying it would issue warnings in comparable situations on the basis of observed atmospheric pressure changes. Understand what that concession actually admits, because it is the point this whole century of incidents has been building toward. Japan's tsunami warning system is the best in the world, and it is fast in a way that took decades and a great deal of grief to build. It can have a warning out in about 3 minutes. It does that by reading the seismic waves, computing a magnitude, and running that magnitude through models that convert it into an expected wave. The chain is earthquake, magnitude, forecast, warning. Every link depends on the one before it. A volcano does not put the right input into the top of that chain. Sometimes it puts in nothing at all, as at Tonga, where the source was an explosion and an atmospheric shock rather than a fault rupture. And sometimes, which is worse, it puts in something that looks like a perfectly ordinary small earthquake. And the model does exactly what it was designed to do. and produces exactly the wrong answer. That second case is not hypothetical, and it is not new, and it has been happening in this specific arc, at one specific spot, roughly once a decade, since at least 1984. Near the southern end of the Izu chain, past Torishima, past the last of the inhabited islands, there is an object called Sofugan. On a chart, it is a dot. In reality, it is a bare column of rock about 100 meters high, standing alone in open ocean, the eroded core of a volcano, whose flanks the sea has already taken, and it is one of the loneliest-looking things on the surface of this planet. European charts called it Lot's wife, which is a decent description of a pillar of stone standing in the middle of nowhere. That whole stretch of sea floor, from Torishima down past Sofugan, is studded with submarine calderas, structures 8 or 10 kilometers across sitting in open water with nothing above them. One of them has a habit. In 1984, an earthquake in that area produced a tsunami that was far too big for it. In 1996, it happened again. In 2006 again. On the 2nd of May 2015, an earthquake of about magnitude 5.7, which anywhere else would be an event nobody outside seismology would notice, produced a tsunami that put around half a meter of water rise onto Hachijojima, close to 300 kilometers away and populated. Half a meter does not sound like much until you consider what it means for the warning system. A magnitude 5.7 earthquake should produce essentially no tsunami at all. The models are not broken. The models are correct for what they were built to describe, which is a fault slipping under the sea floor and displacing the water above it in proportion to the energy released. Something out there was displacing far more water than the seismic energy accounted for, over and over across 3 decades. In 2018, a research team led by Yoshio Fukao published an explanation in the journal Science Advances, and it is one of those explanations that immediately reorganizes everything around it. A caldera is what is left when the roof over a magma chamber collapses. The floor drops, and the boundary it drops along is a ring fault, a roughly circular fracture running down around the whole structure. That ring is still there afterward, and it is a weakness. Now push magma back in underneath. The floor of the caldera is a slab of rock several kilometers across, sitting on a ring of pre-broken ground with rising pressure beneath it. It does not lift evenly like a piston, because nothing in geology is that tidy. It hinges. One arc of the ring fault gives way, and the caldera floor tilts upward along that side while staying attached along the other, like a trap door being pushed open from below. That is the mechanism Fukao and colleagues reconstructed for the submarine caldera responsible in the waters near Torishima, using seafloor pressure records and seismic data. And once you see it, the numbers stop being contradictory. An earthquake's magnitude is a measure of the energy radiated as seismic waves, and that depends heavily on the area of the fault, the amount of slip, and the stiffness of the rock. A trapdoor event happens on a small, shallow, near vertical structure in hot volcanic rock, which is a combination that radiates seismic energy poorly. So the seismometers report something modest. A tsunami does not care about radiated energy. A tsunami cares about how much water you moved, and moving water is about vertical displacement times area. Tilt a slab several kilometers across upward by a couple of meters, and you have lifted an entire column of ocean, all of it, all at once, and that water has to go somewhere. Small earthquake, large wave. Not a paradox. 2 different quantities that usually track each other, and in this specific geological situation, do not. And it recurs, because magma recharge recurs. The caldera fills, the floor tilts, the pressure releases, and then it starts again, on a timescale that has produced these events in the waters near Torishima in 1984, in 1996, in 2006, and in 2015. That is roughly once a decade, at the same spot with the same signature, in a documented scientific literature, Which brings us to the 1st of October 2023, when the seismographs south of Tokyo started registering a swarm. Not one earthquake, a swarm, which is the specific term for a cluster of events with no clear main shock going on. And swarms are the classic signature of fluid movement in volcanic systems, because that is what magma and hot water do when they force their way through fractured rock. The events were in the area around Torishima, out past the last inhabited island in the chain, in water where Japan has no cabled seafloor observatory network, no permanent instruments on the vent, and the nearest inhabited island more than 200 kilometers away. The swarm ran for days. It intensified. And on the 9th of October, a run of shocks in the magnitude 4 to 5 range, with reports of a somewhat larger event, did what that caldera does. Nobody on land felt anything worth mentioning. There was nothing to feel. An earthquake of that size, 600 kilometers offshore, is not an event for people in Tokyo or Chiba or Kochi. It is a line in a catalog. Then the water started coming. Tide gauges up and down the Pacific face of Japan began recording rises that had no business being there. At Hachijojima, the figures came in around 60 to 70 centimeters. Along the Izu Islands, 40 to 50. And then further, and this is the part that made it a national event rather than an island one, measurable waves along the mainland coast, on Chiba, on the coasts of Shikoku and Kyushu, hundreds of kilometers apart from a source nobody had registered as dangerous an hour earlier. The meteorological agency issued tsunami advisories, and it kept issuing them, expanding the coverage through the day as the observations came in, and did not clear them all until the evening. The advisories were not driven by a magnitude calculation, because the magnitude calculation said there should be no tsunami. They were driven by the numbers coming off the tide gauges. The warning system was reading the wave, not the source. Sit with that for a second, because it is a genuine reversal and it deserves to be stated without softening. The best tsunami warning system on Earth, in the country that has invested more in this problem than any other, spent the 9th of October 2023 in reactive mode, telling people about waves that had already been generated and were already measurable, because the thing that generated them did not produce the signal the system is built to read. 60 centimeters is where most people stop paying attention, and that is a mistake that kills people every few years. 60 centimeters of tsunami is not a wall of water on a beach. It is the entire harbor rising and falling on a period of several minutes, which produces currents through the entrance and around the breakwaters that can run faster than a person can swim and faster than a small boat can motor against. It snaps mooring lines. It surges boats against quays and drags them out again. It sweeps people off breakwaters, out of shallows, off the exposed rocks where fishermen stand. Japan issues advisories at that level precisely because the danger at that level is real and specific. And it falls almost entirely on the people whose work puts them at the waterline. So along the Izu Islands and on Hachijojima, with its 7,000 residents, the 9th of October meant getting off the harbor walls, getting boats secured or moved, suspending ferry operations and waiting, without any real information about what had caused it or whether the next one would be bigger. That last part is what makes it worse than a conventional tsunami advisory. After an earthquake, you know what happened. There was a rupture, it has a size, aftershocks decay, and the system has a shape you can reason about. On the 9th of October 2023, there was no such shape. The seismic events were continuing. Nobody could say whether the source was finished because nobody could say with confidence what the source was. And that uncertainty was not resolved that day or that week. It took 11 days. And the thing that resolved it was an aeroplane. On the 20th of October 2023, a Japan Coast Guard aircraft flying a patrol near Torishima looked down and saw a line on the ocean, floating pumice, in a continuous band, roughly 80 kilometers long, with discolored water at one end. That was the first physical confirmation that a submarine eruption had occurred. 11 days after the water rose along 1,000 kilometers of Japanese coast, an aeroplane found the volcano. Take a moment to notice why it took 11 days, because the answer is not incompetence and it is not bad luck. It is the surveillance method. For the far southern part of this arc, the way Japan checks on its submarine volcanoes is by sending an aircraft out to look, periodically, not continuously. There is no cabled seafloor network down there. There are no permanent instruments on those vents. Satellites see the surface, and the surface only shows you something if there is something on it to see, in daylight, without cloud. So the date on which anyone found the eruption is not the date the eruption happened. It is the date a flight went out, in weather good enough to see the water over the right piece of ocean. The 80-kilometer line is itself a piece of evidence, and it is worth reading. Pumice does not come out of a vent in an 80-kilometer strip. It comes out in a patch and gets stretched by the current, which means that line is a record of time. Whatever produced it had been producing it for a while, and the ocean had been drawing it out into a ribbon while nobody was watching. The volcano had been at work, at some unknown level, for some unknown fraction of those 11 days, and possibly for longer. Navigational warnings went out. Mariners were told to keep clear of the area. And the ribbon kept drifting north, up the chain, toward the Izu Islands and the shipping that uses that water, which finally answers the question that has been open since the water started moving on the 9th of October. What warns you when the earthquake is the wrong size for the wave? Nothing does. The wave warns you. That is the entire answer. And it is not going to improve much in the near term because the alternative would require permanent instrumentation on the seafloor at a volcano 600 kilometers out in the Pacific, in 9,000 meters of neighboring water, on a structure that periodically tilts several meters and erupts. Japan has built exactly that kind of network where the megathrust threatens the mainland, because that is where the tens of thousands of casualties are. Down the volcanic arc, the monitoring is periodic aerial patrols and whatever the tide gauges catch after the fact. So the modern system, at its best, works like this. The caldera tilts, the ocean lifts, the wave travels for however long it takes to reach an instrument, the instrument reads it, an advisory goes out, and people who are already within reach of the water get told to leave it. That is genuinely valuable, and it saves lives, and it is also the reverse of what a warning is supposed to be. Now put a vessel in trouble out there and walk through what actually happens, because this is where the century of accumulated capability meets the geometry that has not changed since 1841. A boat 200 kilometers south of Hachijojima loses her engine, or takes damage, or starts flooding. In 1952, nobody would have known. Today, the beacon goes off. The satellite hears it within minutes. The alert lands at a coordination center carrying the vessel's identity and a fix good to within the length of a football pitch, and the response begins immediately. That is a genuine transformation, and it deserves the credit. Then the geometry takes over. Fixed-wing Coast Guard aircraft can be over the position within a couple of hours, which is fast and which cannot lift anybody out of the sea. A helicopter is what lifts people out of the sea, and helicopters have a range problem that nobody can engineer away. Fuel burned going out is fuel not available for searching, hovering, or coming back. And hovering to recover survivors is the most fuel-hungry thing a helicopter does. Mainland-based aircraft cannot reach the southern end of this chain and return with any useful time on scene, which means the realistic rescue asset is a surface vessel. A patrol vessel making 20 knots covers 200 kilometers in about 5.5 hours, and that is if she happens to be at the right end of her patrol area when the call comes, which she usually is not. 600 kilometers out toward Torishima is 15 or 16 hours. From Chichijima further still. So the honest number for a serious incident in the middle of this chain is most of a day between the alarm being raised and a ship arriving that can do anything about it. Then, the approach. Whatever caused the emergency is generally still happening. A crew coming alongside a disabled vessel in the short, steep, breaking seas this region manufactures out of a moderate northerly is doing one of the more dangerous evolutions in seamanship, and the option to simply wait for better conditions is bounded by how long people can stay alive. And the aeroplane that can land on the sea, the amphibian that has been pulling patients off Ogasawara for decades, is limited to roughly 3 meters of wave height. On a day when it is genuinely needed, that limit is frequently exceeded, and when it is exceeded, the aircraft does not land, and the fastest link in the entire chain is simply unavailable. It is not broken. It is not underfunded. It is a piece of extraordinary engineering meeting the shape of the water. Every one of those constraints is the same constraint that shaped the earlier stories. There is no shelf to shelter on. There is no anchorage to hold in. There is no coastline to run for. The nearest useful help is hundreds of kilometers away and traveling through the conditions that caused the problem. Technology has compressed the time between something going wrong and somebody knowing about it from days to minutes, which is an enormous achievement. It has not compressed the distance at all. The distance is the same distance it was when a whale ship out of Massachusetts happened to stop at Torishima for turtles. And people keep going out there for reasons that have not changed either. The fish are still concentrated over the seamounts, because the seamounts still push deep water into the light. The islands still need supplying, because people still live on them. The charts still need correcting, because the sea floor still moves. The birds still need someone to haul their chicks to safer ground. The volcanoes still need watching, and watching them means flying out there and looking. The ark is not finished either. It is not a historical hazard being managed down to nothing. It is actively building. 1,000 kilometers south of Tokyo, in the Ogasawara group, there was an island called Nishinoshima that for most of the 20th century measured less than a third of a square kilometer, a rock with some vegetation on it. In November 2013, a new vent opened in the water just off its southeastern side and started building. Within weeks, the new cone had joined the old island. Then it kept going. It went on and off for years, and in the phases when it was active, it produced lava at a rate that buried the original island completely under its own new ground. By 2020, Nishinoshima had grown to more than 4 square kilometers, more than a dozen times its former size, with a cone rising a couple of 100 meters out of the sea and ash columns reaching 8 kilometers. Japan got bigger. Not as a manner of speaking. An island generates a territorial sea around it, and a permanent one generates more than that, so the national extent of the country was materially altered by a volcano nobody can stand on. And the way that has been observed for over a decade is that the Japan Coast Guard sends an aircraft, and people look out of the window and take photographs, and specialists study the pictures. Ships hold their distance. Nobody lands except in carefully chosen moments on the surviving edges because the ground is new and hot and unstable, and the vent does what vents do. The most significant piece of new Japanese territory created in a lifetime is monitored the way an unexploded device is monitored, which is, in the end, the honest description of this entire stretch of ocean. Set out what is actually operating, because none of it is mysterious and all of it is permanent. The geography establishes the rules. A cold, old, heavy plate is sinking into a trench that falls to nearly 10,000 meters, and about 200 kilometers west of that trench, the melt it releases is building a chain of volcanoes 1,000 kilometers long, of which only the tallest peaks reach the air. That arrangement gives you 2 things at once, and they are the same thing: extreme depth and extreme shallowness within sight of each other, and nothing in between. No bank to anchor on, no bay to duck into. A vessel in trouble here has nowhere to go, not because she is far from land in the ordinary sense, but because the land in this region is either an active volcano or a cliff without a harbor. The weather activates the rules. In winter, cold continental air pours out over a warm western boundary current at a temperature contrast among the largest on the planet, which builds storms with unusual speed and drives a persistent wind against a current running the other way. That opposition compresses wave spacing and steepens the faces, which turns unremarkable forecast numbers into seas that hit small hulls instead of lifting them. A crew reading 25 knots and 3 meters on the forecast is not reading a warning. They are reading a working day, and on the wrong side of the Kuroshio front, it is not one. Human motive supplies the exposure, and it has never had to be dramatic. Feathers, because they were worth money and the birds did not run. Sulfur, because it was underfoot. Fish, because the same seamounts that can detonate are the ones that push nutrient-rich water into the sunlight and concentrate a catch into a findable area. Charts, because a maritime nation is obliged to know where its hazards and its territory are. Transport, because people and cargo have to cross this ocean. Supply, because 2,500 citizens live at the far end of it. Even conservation, because the last stronghold of a species that was nearly exterminated sits on an unstable ash slope that has to be actively managed by people who fly and sail out to do it. Technology changes what is possible and consistently redistributes the risk rather than removing it. Position is solved and distress alerting is close to solved, and neither shortens the 200 or 600 kilometers a rescue vessel has to travel. Satellites see a plume in 10 minutes and cannot see a loaded vent under 50 meters of water. Seismic warning is world-class and depends on the source producing an earthquake proportional to the water it moves, which a tilting caldera floor does not. Engines gave crews independence from the wind at the cost of a permanent dependence on a fist-sized hole in the hull, which a volcano can plug from 1,300 kilometers away. Every improvement is real. Every improvement has an edge, and the edges are where the casualties still occur. Distance sets the ceiling on all of it. That has not moved since 1841, and it is not going to. The chain is 1,000 kilometers long, and the help is at the top of it. And the history is not a set of anecdotes, it is a repetition rate. Aogashima in 1785, Torishima in 1902, Myojinsho in 1952 and 1953, the observatory driven off Torishima in 1965. Oversized waves out of the caldera field near Torishima, 4 times since 1984. Fukutoku Okanoba building and losing islands in 1904, 1914, 1986, and 2021. Nishinoshima since 2013. Torishima again in 2023. These are not coincidences accumulating. They are one machine cycling, and the intervals are short enough to show up in a single human career and long enough that each generation gets to be surprised. So return to the question this started with, because it has an answer now. Why does the one stretch of ocean Japan surveys most carefully keep killing the people it sends to survey it? Because the object being surveyed does not hold still. Not over centuries, over days. A chart is a claim about where something was when somebody measured it. Down this arc, the ground rises and falls through the sea surface on the timescale of a working trip, and the state in which it is most likely to kill you is the state in which it is invisible. A heap of loose new rock sitting just under the waterline, at the exact depth where seawater-reaching magma flashes into steam with maximum violence, between pulses, showing nothing. The most dangerous condition this ocean produces cannot be drawn. It has no position that stays true, no depth that stays true, and no surface expression at all until the moment it becomes one. Then there is the second half of it, which is that the hazard travels. A volcano that stops erupting has not stopped. It has handed its output to the current, and the current runs 3 or 4 knots, and it will deliver floating rock to a harbor 1,400 kilometers away in October and to Tokyo Bay in December. It will carry a tilting caldera's wave to 4 separate coastlines in a morning. It will take a boat's wreckage 150 miles downstream before anyone has finished filing the paperwork that says she is overdue. None of that is supernatural. And the people who dressed it up as supernatural did real damage, because the dressing up made the correction possible, and the correction persuaded a great many people that there was nothing here at all. There is something here. It is documented, it is physical, it is recurrent, and it is currently under-instrumented for exactly the reason everything remote is under-instrumented. Almost nobody lives there. The ferry still leaves Takeshiba on schedule, 24 hours to Chichijima, roughly once every 6 days, and the people aboard are ordinary people going home or going to work. The fishing boats still work the seamounts, because that is where the fish are. The Coast Guard still flies the patrols, because a periodic look from an aircraft remains the best available method of finding out whether a volcano 600 kilometers offshore has started doing something. The amphibian still sits ready for the next medical call from an island with no runway, still bounded by 3 meters of wave height. And on Torishima, where 125 or 150 people were killed in a single morning in 1902, somebody is still walking chicks across an active volcano to keep the slope from taking them. The last picture in this is the one from the 20th of October, 2023. A Coast Guard aircraft out past the last island anyone lives on, banking over open ocean. Below it, a thin gray line on the water, 80 kilometers long, drifting slowly north toward the shipping lanes. Discolored water at one end of it, fading into blue, and nowhere in the frame, on any part of the surface, is there a volcano to see.